pleasure to introduce for Bar-Natan, who will tell us about Chern-Simons-Witten theory near the co-commutative line.
Okay, so first of all, my talk follows a handout. I hope you're all holding a copy. Second, there is a URL where there is a copy of the handout, and later there will be a video of the talk and all sorts of other information. It's that one. Oh my God, I forgot to reload. Right before, while preparing, I realized that I postponed one of the key points to the very end, and I decided to push it to the beginning. So I'll tell you the key point without any context, or one of the key points without any context, and the context will come later. So the claim is that semi-simple Lie algebras fit into one-parameter families of Lie algebras that at 0 are easy, and at epsilon not equal to 0 become your semi-simple Lie algebra, which is actually hard. Okay, so for example, or here's how it comes about. So take for example GLN, and in fact to understand GLN, no, but that's good enough. To understand GLN, it's enough to understand half of GLN, namely the upper triangular matrices. Because you see, GLN, if you think of it as square matrices, you can also think of it as the direct sum of the upper triangular with the lower triangular. You get the diagonal doubled, but that's relatively mild. It turns out that the second copy is commutative, or commutes with everything else. And then the lower diagonal matrices, the lower triangular matrices are dual to the upper triangular matrices. And so the upper triangular matrices have both a bracket, and as the dual of the lower triangular matrices, they also have a co-bracket. So the bracket is just a map from upper triangular tensor upper triangular to upper triangular, and the bracket of the dual, the bracket of the lower triangular, leads to a co-bracket, which is a map from the upper triangular to the upper triangular tensor upper triangular. Now, there is a way of recovering GLN from just the upper triangular matrices and the bracket on the co-bracket, and it's called the Drinfeld double operation, or maybe the Manning double operation. I'm not quite sure what's the right way to call it when the context is Lie algebras. But basically, you take the direct sum, and then on the direct sum, there is a way to induce a Lie algebra using B and delta. And basically, and the key point that I will come to later is that you can define GLN epsilon to be the same thing, but replacing the co-bracket with epsilon times the co-bracket. Really what it amounts to is to say that the bracket remains the same. So if you take the bracket of an upper triangular matrix with an upper triangular matrix, the result is as it used to be. If you take the bracket of a lower triangular matrix with a lower triangular matrix, you multiply the result by epsilon. And if you take the bracket of an upper triangular with a lower triangular, the result is a sum of two things. A part is a lower triangular, and a part is an upper triangular, and the upper triangular gets multiplied by epsilon. Now, that same process works for all semi-simple algebras. Basically, replace the word upper triangular and lower triangular by upper Borel and lower Borel. And the point is that when epsilon is away from 0, so when epsilon is invertible, the result is the same Lie algebra you started from. So you didn't lose anything. But when epsilon is equal to 0, or when some power of epsilon is equal to 0, the result is a solvable Lie algebra. And solvable actually means exactly that. You can solve it. So basically what I'm going to tell you is that it makes sense to start with GLN epsilon rather than GLN, and perturb around epsilon equal to 0 where things are easy. Okay? And I will call this either the co-commutative limit, because as epsilon goes to 0, you're starting from a co-commutative Lie algebra, or the solvable approximation for obvious reasons. Okay?
Draw a question.
Yeah.
Should I think about epsilon as a number or as an operator? Because epsilon k plus 1 to the 0, if it's a number, I don't have anything else.
It's a formal parameter.
It's a formal parameter.
It's so really, I will do everything. Everything will be power series in epsilon.
Okay.
And saying epsilon to the k plus 1 is equal to 0 means that you study the power series only up to power epsilon.
Oh, I
to
see.
the k.
I see. It's the truncation in the.
Yeah.
Okay.
Okay. Anyway, now back to the beginning of my talk. So again, first of all, maybe I should say I'm an outsider here. So and maybe that was the intent. You know, maybe every talk should have some every conference should have some outsiders in it. And basically, I do the opposite of what you're trying to do. You're trying to use nature in order to compute quickly, and I'm trying to find approximate nature, maybe meaning take the limited or take epsilon b, consider epsilon as small, or crop at high powers of epsilon, which amounts to saying that I'm approximating nature. But I want to tell you that I can approximate certain parts of nature. I can approximate by means in ways that can be computed quickly. More specifically, I will tell you how to do it in the case of the Chern-Simons-Witten theory, and or I aim to tell you how to do it for the Chern-Simons-Witten theory. And I really wish I could talk in the language of the Kabbalah, but unfortunately I'm not smart enough for that. So I'll just highlight the Kabbalistic points and stick to the Talmud. But since some of you don't know what I'm referring to, here are the definitions. So the Talmud is the basically rigorous Jewish law, the body of rules and regulations and justifications for them. And if you want to think what I mean, well, basically I'm clearly referring to rigorous mathematics. Kabbalah is Jewish mysticism, and clearly I'm referring to path integrals. Okay? So, and if we're at it, it's kind of famous that Kabbalah is not recommended for people under 40. And I'm going to do even worse than that, because I'm going to do speculations around Kabbalah. Okay? And I suppose my justification is that, first of all, I am over 40. And second, the speculations I will tell you about lead to results, lead to Talmudic results. So it's really not an open-ended speculation. Maybe we will do some Kabbalah and the gods will be with us, but it's really a speculation about where things are coming from. Okay, where the results that are already there, where are they coming from? So I will have an overall map, and the overall map is basically the old Chern-Simons theory map, which, after replacing the Lie algebra by G sub epsilon, which I've already defined, becomes a new Chern-Simons theory map. And again, the old has its Kabbalah part and its Talmud part, and the new has its Kabbalah part and the Talmud part. But since all of this will look so crazy, I think I will want to tell you first, okay, so I'm going to, the thing I'm really missing is the Kabbalah that goes from here to here. And I want to start with this, which is completely Talmudic. Okay, just so that you know that the place I'm heading to is not insane. Okay? And in particular, I want to start with the results, and the resolution is not good enough, so turn to page 3 of your handout, and here's the same thing in higher resolution, and here are the results. Okay, so I am going to define an invariant, which is an ordered pair delta comma theta. It's called uppercase theta, and it's an ordered pair delta comma theta, where delta is actually the old Alexander polynomial and theta is the main point. So delta takes values in polynomials, Laurent polynomials in a variable t. Theta takes values in Laurent polynomials in 2 variables, t1 and t2. And the first thing I want to tell you is that it's a strong invariant. So here is a tabulation of various not invariants computed against knots with various numbers of crossings up to 10, up to 11, up to 12, or up to 15. And the entries in the boxes are the deficits. So basically, if you look at the hyperbolic volume and see how many different values it attains on the 300,000 knots with up to 15 crossings, you see that it attains, well, I don't know how many values it attains, but the number of values is 43,000 less than the number of knots. So basically, it misses 43,000 knots or so. Yes?
So the coefficient of the Alexander polynomial finite type invariants. Are the
Yes.
second one also? The coefficient of theta, are they also finite type invariant?
Yes.
They are? Okay.
Yes.
So they are efficient computable then.
No.
Really? I thought you have a theorem.
Coefficients of finite type finite type invariants are extremely inefficiently computable. So, to be interesting, you have to look at a high degree. So, an invariant of type D can be computed in time n to the power d, which is polynomial in d. Polynomial in n.
Okay.
Okay? But and recently we have a paper that says that it's actually n to the d over 2.
Okay.
Okay? But still, it gets interesting only when d is very high.
Yeah, so the coefficient is hard to compute.
So if you want if you want to get something strong out of finite type invariants, you have to look at the first 100 finite type invariants, or first large number of finite type invariants, and then you get polynomials that look like n to the 50. Okay, and these are not polynomials. Okay, in practice. Okay?
In theory, they are.
In theory, they are. In practice, they're not. Okay, so again, here is a table of common invariants, and here is a list of standard invariants: the Homfly polynomial, Chovanov homology, the volume, and other things. And it has a deficit of 41,432. And the invariant theta that I'm going to, basically you can tell the jump. The invariant theta has a much lower deficit than all of the other things taken together. And if you add all of the other things to theta, the deficit doesn't shrink by much. So theta is strong. Next, theta is fast. So yes, it's polynomial time, but it's, I don't really care that it's polynomial time. It's actually fast to compute. So if you take a 300 crossing knots, and I took a random one, and I'm not showing you the picture because the diagram, because it's just not informative, okay? But anyway, if you compute theta of a 300 crossing knots, the computation runs. You can compute theta for a knot with 300 crossings. And this more or less proves that I don't belong here, because it means that theta does not come from some R matrix, TQFT, tensor category, because then you'd have to look at tensor powers of Hilbert spaces, and the dimension would be impossible. You will not be able to compute anything. So this more or less proves that I don't belong here. Anyway.
I'm not sure. Maybe it's a lattice root of unity, so.
Well,
anyway.
Or like the crystal limit. Like, I mean, presumably this doesn't have anything to do with crystal, like quantum groups at Q equals 0.
I don't know that it has anything to do. Okay? Anyway, no, it does have to do with quantum groups. I will show that later. But it's not the part of quantum groups that quantum computing cares about. Anyway, here is the output for a 300 crossing knot, and let me explain it. So, as I mentioned before, theta is a pair, a Laurent polynomial and a Laurent polynomial in two variables. A Laurent polynomial in one variable is basically a sequence of coefficients, and you can think of these coefficients as defining colors, let's say red for positive and blue for negative, and then the invariant becomes a barcode. And in fact, I fade out the low coefficient, so it becomes a barcode with like a little bit extra information. Now, if you take a two-variable polynomial, so a two-variable Laurent polynomial is an array of coefficients, and that becomes an array of pixels that can be red or blue, and again, also with some color, with fading. And if you look at the, and that just means a QR code or a picture. So if you look at the picture corresponding to that random 300 crossing knot, it comes out to be the picture over here. But this picture is, well, there is symmetry in it, but it's not manifested, it's not obvious, or it's a bit tilted. So basically, what we do is we shear the picture and print it this way, and then it comes out a perfect hexagon with hexagonal symmetry. Okay? Here are a few further examples. Okay, this is the trefoil, and in fact, here each box is marked with what monomial it corresponds to. Here is the Rolfson table, and I guess you can see patterns in it. Most of them I still don't understand. Okay, here are some torus knots, and here are some random knots with 51 to 77 crossings. I mean, I could compute 300 crossings. We did. I have a picture like that with knots with 300 crossings, but then it's a bit harder to see.
George, this is on
Okay.
Not Atlas, the data with
The data is at omega epsilon beta slash dk. And omega epsilon beta is defined at the top of the handout. Okay? Now, you know, if you know Chladni pictures, Chladni figures, so these are, you know, if you put sand on a plate and shake the plate, you get funny pictures, okay, depending on the frequency of shaking. And these look vaguely like that, and I have no idea why. And then, yeah?
I have a map from integers into two colors.
Yeah. So basically, positive integers go to red, negative integers go to blue,
0.
and 0 goes to white. And like large positive numbers are bolder colors.
There's almost no white. There's only white at the boundary.
No, the boundary is just boundaries that I left artificially.
But then there's no white.
But there is, yes, there is almost no white here, but like for torus knots, there is a lot of white. Okay, like look at this one. Okay. I guess my next claim is that this invariant is fun. And fun means two things. First of all, I think the pictures are fun. And second, there are lots of things that we still don't know. And, you know, we're planning to work on it in the next few years, and you're welcome to join. And the last thing to say is that in the result direction is that the invariant is meaningful. So theta gives a genus bound, and we can prove it, but the proof is not yet written. We have experiments, but it's rather safe, so on a very large number of knots, showing that theta give a fibered criterion, a criterion for a knot to be fibered. So basically, it somehow it sees topology. By the way, this is something that's very hard to say about the Jones polynomial. Okay, so it actually sees topology. And we hope theta is related to the so-called two-loop invariant of the that comes from the Kontsevich integral, and we hope that theta will say something about ribbon knots, but this is not done yet. Okay, so back to the overall map. And again, I still want to start from the Talmud, so I still want to talk mostly about the Talmud rather than the whole map, which is Kabbalah. And so we have a theorem and we have a proof, and I already told you about the results, so the next thing is to tell you about the theorem. So the theorem is really, how is the invariant defined? Okay? So first of all, conventions. So T1, and T2 are variables, and T3 is defined to be T1 times T2. Second, so suppose I want to compute the invariant of some knot. The first thing I do is I draw it in the plane as a long knot, and I cut it open, and I draw it in such a way that the entering point, the beginning point, is pointing up, the knot is pointing up. At the output, the knot is pointing up, and at each of the crossings, the two strands that arrive at that crossing are pointing up. And of course, I can always do it because, you know, if a crossing is not pointed up, I can just tilt it to point up. Okay? But the point of doing this, okay, sorry, before that, then I label each of the edges of this diagram with two indices. So 1, 2, 3, 4, 5, 6, 7, that's just a sequentially running index. And the second thing is, so you see each edge begins pointing up and ends pointing up. And if you have an edge that begins pointing up and ends pointing up and you follow it, then it has a rotation number. It has a well-defined rotation number. So I'll call these rotation numbers phi sub k, where k is the index of the edge. So here phi sub 1 is 0, phi sub 2 is 0, phi sub 3 is 0. The only interesting rotation number is phi sub 4, and it's -1 because edge number 4 does a full clockwise rotation in this picture, and that's the end of the preparation phase. Okay? Next, I have to tell you about Model T traffic rules. And I think you have papers about that.
Yes, but I've just said the preparation have nothing to do with the braid group. It's just
No.
just
no.
a
It's
one
not,
knot diagram.
it has nothing to do with the braid group.
Okay,
the knot
good.
is not a braid group.
Yeah, okay. It's just a 1-1 tangle.
Yeah.
Okay.
Yeah. I mean, this one is a braid group.
Yeah, that's
but in
what
general,
confusing.
It doesn't have to be a braid group.
Yeah. Okay.
Okay? So here are the traffic rules. So cars can drive on knots. When they drive on a knot, they always drive following the orientation of the node diagram. And when a car, wait, I think when a car comes into an interchange, namely a crossing, well, if it comes on the lower strand, it just passes through. But if it comes on the upper strand, it falls down, it passes through with probability t, where t is a number close to 1, where I think of t as being close to 1, and it drop downs with probability 1 minus t. So basically, here is a crossing. If a car enters here, or if I inject car traffic on the lower strand, and I put traffic counters on the upper strand, on the outputs, then this traffic counter will measure traffic amount 1, and this traffic counter will measure traffic amount 0. However, if the car enters on the upper strand, then the counter here will measure t, and the counter here will measure 1 minus t. Now, this is for positive crossings, and for negative crossings, again, if I enter on the lower strand, I just pass through, and if I enter on the upper strand, then I pass through with probability t inverse, and drop down with probability 1 minus t inverse, and you can complain that t and t inverse cannot be probabilities at the same time, and I really don't care, because I'm not using the interpretation of probability as numbers between 0 and 1. I'm only using the rules of probability, that the sums of events have, or this joint event has probability, the sum of the events, and, well, basically I'm only using the algebraic side of probability theory. And then finally, when cars come to the end of the knot, they drop out and disappear. And then let me define the traffic function of a knot, and let's call it G, or G alpha beta. So alpha and betas are indices of edges on the knot, and then G alpha beta is the amount of traffic, or the amount that the traffic counter placed at beta will measure, assuming that you're injecting traffic at alpha, with the further convention that if alpha and beta are equal, you inject the traffic at the point before the point where you measure. Okay? And likewise, so this is model T cars. Likewise, there are model T nu cars for nu equals 1, 2, or 3, and it's exactly the same, except T is replaced by T1 or T2 or T3. And so I get a traffic function G nu alpha beta, and nu is only 1, 2, or 3. Okay? And maybe I'll start with an example. So suppose my knot, well, it's not really a knot, my knot diagram is just a kink, and I inject traffic at position 1, at edge number 1, then a counter on edge number 1 will measure 1. A counter on edge number 2 will measure, well, every car that starts here goes through, because this is the understrand, so it will measure 1. And then the cars come up on the upper side, and with probability t, it drops down and gets measured the second time, gets counted the second time. So you'll be counting 1 plus t. But then it goes again through the overstrand, and with probability t squared, it drops down a second time. With overall probability t squared, it drops down 2 times. And then it gets counted a second time. So basically, it passes with probability t. So it drops down with probability 1 minus t. So basically, what you measure here will be the sum over p of 1 minus t to the p, and that's a geometric series whose sum is t inverse. And finally, all of the cars, before disappearing, pass through the last traffic counter, so this traffic counter measures 1, and they pass through it exactly once. Okay, if you inject the traffic on edge number 2, then edge number 1 will count 0. There is no way to get there. And the computation for edge number 2 is the same as before, so it will measure t minus 1, and the last edge will measure 1. And finally, if you inject traffic on edge number 3, then edge 1 and 2 will measure 0, edge 3 will measure 1. And so the traffic function, or the traffic matrix, is the matrix 1 t inverse 1, 0 t inverse 1, 0, 0, 1, and it's written here. Yeah.
So I'm assuming this is only for knots, and if I wanted to do it for links, I'd have to cut open each link independently to get like a block triangular thing. Is that correct? Or is that...
For links, no, you actually still cut open only one component.
Only once, okay.
Yes, and it's a bit, and there are issues with well-definedness.
Okay.
It's not defined for all links. It's defined only for links for which you don't end up getting infinite loops of traffic,
I see.
which amounts to saying that some matrix has to be invertible. Okay? So here's the theorem. So first of all, a crossing for me is a triple Sij, where S is the sign of the crossing, and I is the label of the incoming upper strand, J is the lower of the incoming lower strand, and that it doesn't matter if it's a positive or a negative crossing. So if it's a positive crossing, I is on the left and J is on the right. If it's a negative crossing, I is on the right and J is on the left. I is always the upper strand. And then the claim is that there is a quadratic function Q1 depending on, sorry, not Q1, called F1, depending on a single crossing, so depending on S, I, and J of a single crossing, and it's quadratic in the G nu alpha beta. So it contains, at the most, a product of 2 G nu alpha betas. There is a cubic function, similarly, which depends on 2 crossings, it's a cubic function, again, in the G nu alpha betas, and then there is a third function, which I believe is linear, depending only on the rotation, one edge and its rotation number. And then you define theta of a knot diagram to be a certain normalization, which I will mention before, and it's easy to compute, multiplied by a single sum over the knot of F1 of C, plus a double sum over the knot of F2 of C0 and C1, plus a single sum again over the edges of the knot of F3. Now, if you knew the traffic function, I'll figure out the traffic function in a minute, but if you knew the traffic function, this computation is, this is basically a double sum on the knot. It's quadratic amount of terms, and each of the summands here is finite. Okay? So this is a very easy computation to carry out. If you want some pictorial interpretation, maybe the most interesting picture is the picture corresponding to the middle term. So you have 2 crossings. It's a summation over pairs of crossings. So you sum over, this is crossing number 0, this is crossing number 1. And basically you sum over the amount of traffic of type T3 that starts near the left crossing, and you measure it near the right crossing. And at that point, a car of type 3, in your mind, breaks into a car of type 1 and a car of type 2, and these 2 cars will start here and gets counted here, or maybe recombine into car number 3, and basically you measure the amplitude of that. Now, there are actually quite a few terms that are possible, because you could start in any of the edges around this crossing, and you can measure on any of the edges around this crossing. So there are actually quite a few terms here, but they're all schematically of this theta type, and this type is what gives the diagram its name. Now, these pictures should remind you of Feynman diagrams, and I will try to justify it later. Okay, yes?
It's obvious this won't be determined by the fundamental group. I hope it's not.
I don't know why you hope it's not. Okay, first of all, I don't know how it's determined by the fundamental group, but the fundamental group is almost a complete invariant of naught. So if it's so if you can extract some information that was not extracted before from the fundamental group, that's good news.
Well, if it's fundamental group, I would guess the lower central secrets. So that would be go back to like a
No, but
Milner.
it does not. But okay.
Anyway,
Now let's go back to the normalization constant. The normalization constants are just the Alexander polynomial.
Okay.
So delta sub nu is the Alexander polynomial at T nu. And you know, even the Alexander polynomial is well, it's not finite type. It's not determined by it's not computed from a fixed quotient in the of the lower
Okay.
central series. Right? Each coefficient is finite type, but the whole thing is not.
okay.
So same here. I mean, yes, this is a polynomial, and in some parameterization, every coefficient will be finite type, but the overall thing is not finite type. So
Okay.
in that sense, it's no different from the Jones polynomial. I mean, the difference is that it's computable, it's stronger, and it's meaningful.
Okay.
Okay? Yes.
But the data of all color Jones polynomials, does it contain this information together over all colors?
No, but colored Humphrey contains this. Okay? But again, colored Humphrey you cannot compute. You can talk about it. You cannot do anything with it. This you can compute for nodes with 300 crossings. Also, you know, colored Humphrey, if it contains topological information, it's very hard to extract. And here we can tell you how it computes the gene, or how it bounds the genus and how it's a fiber criteria. So you know, reparameterizing colored Humphrey is not a meaningless task. It's not like you can say, oh, I know colored Humphrey, I don't need to think about it. You don't know colored Humphrey. Okay? Okay. So I still owe you what are F1, F2, and F3, and this is the ugly news. Okay? Here is F1, here is F2, and here is F3. Okay? And the last thing I owe you, well, I mean, everything depended on knowing what the traffic function is, so I need to tell you how to compute it, yes?
What's the CF that you use in these? The expand elect dot F the factor?
Oh, just bring it into canonical form. It's a mathematica. It's not interesting. This is the function. This is really expand. Okay? Okay. So, how do I compute the traffic function? So, I mentioned before that it's inverting a matrix, so let me explain how it's inverting a matrix. So, basically, first of all, there is something that I'd like to call the G rules. And there are G rules next to each crossing. So if you have a crossing with incoming strand, upper strand I, incoming lower strand J, outgoing upper strand J plus, outgoing upper strand I plus, the G rules are that Gj beta, where beta is any other edge, is equal to Gj plus beta plus a delta function. What does this mean? Really, if you are injecting traffic at J, or injecting traffic at J plus and measuring traffic somewhere else, there's no difference because every car that starts at J goes on to J plus. Okay? So, so Gj beta is more or less equal to Gj plus beta, with one exception, and the exception is if you measure at beta. if you measure at J, because if the traffic counter that you put is at J, then the cars injected at J get counted, and the cars injected at J plus don't get counted, so there is a delta function difference. Similarly, Gi beta is equal to t to the power s, s is the sign of the crossing, Gi plus beta. This is the statement that every car injected at every car going in from I, with probability t gets to I plus, with probability 1 minus t gets to j plus, and again there is a delta function. And if you look at the collection of all of these G rules, basically this one, that one, and then there is a G rule for the ending point. Every car injected at the end point gets killed immediately. This is a set of linear equations that the G's have to satisfy. And really what it says is that G is the inverse of a matrix A, where the matrix A is the 2n plus 1 by 2n plus 1 identity matrix with an additional contribution for each crossing. So if the crossing is Sij, the additional contribution is at row I, row j, column I plus, column j plus, you add this 2 by 2 block. Okay? So for example, for the trefoil, so here is the trefoil. There is a crossing between 1 and 4, a crossing between 2 and 5, and a crossing between 2 and 5, and a crossing between 3 and 6, yellow, pink, and bluish, and they correspond to taking the 7 by 7 identity matrix, adding to it a blue contribution, which is a copy of the matrix written over there, a pink contribution, and a bluish contribution. Sorry, I meant yellow. Anyway, okay. And then the traffic matrix will be the inverse of this matrix, and you just compute it, and it comes out to be that. So how hard is it to compute our invariant? You need to invert an n by n or a 2n by 2n matrix with entries that are polynomials of degree 1, and that's not a hard thing. So you can do it for knots with up to 300 crossings rather easily. Okay? And finally, that matrix turns out to be a presentation matrix for the Alexander polynomial, and so its determinant up to some easily computed power of t is the Alexander polynomial. So the deltas are really there to cancel the denominators, right? Because when you invert a matrix, you get the denominator proportional to the determinant, and if I multiply by the deltas, so by the determinants, I cancel all the denominators. Okay? Okay, so, oh, and maybe one last thing. So it's also extremely easy to implement. So here is a complete implementation. Basically, you make the list of crossing, you let A be the identity matrix, and then for any time within the list of crossings, if you see a crossing of the form Sij, then you add to A in row I and row j, column I plus 1, column j plus 1, a 2 by 2 block. Then you compute the determinant of that matrix, the inverse of that matrix, and then you add the contributions, a double summation for F2, a single summation for F1, and another summation for F3, and you output the results. So the program is really, really, really simple, and that's the program that runs for up to 300 crossings. And, well, here is an example of a run. So this is the result for the trefoil knot, and here are the Conway knot and the Kinoshita-Terasaka knots. And these knots are notoriously hard to separate. Like many other invariants fail to separate them. Well, we do separate them. And like you can see actually that both of them have Alexander polynomial 1. Okay? And, well, okay, I stated a theorem, it better have a proof. Here is the proof. I'm not going into it because I want to go somewhere else, but the reason I'm flashing it is only so that you see, you know, that's the it's not hard. There's not a lot in the proof. Okay? Okay, so I'm back to the overall map, and I want to claim that the invariant, today's invariants, come from Chern-Simons theory, in which you replace the Lie algebra by its solvable approximation, as I mentioned before. But let's start from the classical story before you do this replacement. So the classical story goes roughly as follows. So Chern-Simons theory for a Lie algebra G is the path integral over this. So I'm in R3, so I'm not making a distinction between a connection and a one form. So it's an integral over the set of Lie algebra valued one forms of the exponential of the integral or in R3 of a wedge dA plus 2/3 a wedge a. And usually people put a k constant here. I scale it out and instead put a square root of h bar as the coefficient of the a wedge a. And then I multiply all of this by the trace in some representation of the holonomy of a multiplied by the square root of h, along a curve gamma, which represents your knot. And, well, this is the so-called Chern-Simons-Witten invariant corresponding to a metrized Lie algebra G and a representation V in which I take this trace. Now, there are at least two ways to interpret this. So one way, I should say all of this is in the realm of the Kabbalah for me. So one way is using conformal theory and various other magic, you can turn it into the Reshetichin Turayev invariance of the knot we started from in R3 using a Lie algebra G and a representation V, and at Q equals e to the h. Okay? And I have to say that I don't think this is sufficiently understood. I certainly don't understand it sufficiently. But it's commonly accepted part of the Kabbalah that all of us believe in. Okay? Now, there is a different way to interpret this. And the other way is to use perturb Gaussian integration and Feynman diagrams, and that at the end leads to configuration space integrals. And maybe I should say a word about what that means, okay? And this is the point where I thought I'm very close to Jorgen, but I think he ended up looking at different limits. So anyway, let me basically state the theorem which is at the basis of perturbed Gaussian integration and of Feynman diagrams. So if you want to integrate over x running in R to the m, so you can think of M as either being a finite set or a manifold cross a finite set. And basically, if it's a manifold, it means functions on the manifold. So X is really a function on the manifold. But it's probably easier to think of it as just a finite set. And then you want to integrate a quadratic in X. So some function aij times xij, this should be, divided by 2, plus some small constant times a perturbation, which is some polynomial in X of degree not too high. And then the statement is that the result is 1 over the square root of the determinant of A times e to the GIA del xi del xj, where Gij is the inverse matrix of the matrix A. So this is a differential operator. I apply it to e to the epsilon v and compute this at x equal to 0. Now, if you want to crop at some small power of epsilon, then this is just some power of v. or sum of powers of v, and v is a polynomial of a fixed degree. So this is some polynomial of a fixed degree, and you apply to it a certain number of differentiations. There are only that many differentiations that you can apply before it comes to 0, and so this is in principle computable. And in fact, you can trace the combinatorics, how you carry out this computation, and that's what leads to Feynman diagrams, but I'm not going there, okay? But, okay, this has a Kabbalistic and a Talmudic meaning. So the Kabbalistic meaning is if M is a continuous manifold, and then this is really an integration, not a summation. And likewise, here you get integration, and you end up reducing an infinite dimensional integral to a sum of finite dimensional integrations, and that's the celebrated, that's how quantum field theory works, perturbative quantum field theory works. The Talmudic interpretation, which somehow nobody seems to care about, is the following. So if M is a discrete set, then what this does is, so you see, if M is discrete but still big, this is an exponential time thing to compute if you're naive, right? Because of exactly the curse of dimensionality, right? You have to compute an integral over a high dimensional space. You have to find many, evaluate the integrand at many, many points. The number of points is basically grows exponentially in the dimension of the space. On the other hand, this is just a finite sum of sums that run between, where I and j run in M. So it's a finite sum of sums where you have finitely many indices that run between 1 and M, and that's a polynomial time computation. So basically, Feynman diagrams for physicists, or the Kabbalah Feynman diagrams, reduce path integrals to finite dimensional integrals. The Talmudic Feynman diagrams reduce exponential time computations to polynomial time computations if you are willing to just approximate, so to just look at the finite power of epsilon. Okay? So, that's, by the way, a lovely point. I mean, I hope people will appreciate it. Okay? So, in fact, the invariant I was telling you about before has a perturbed Gaussian integration formula, and here it is. And here it is at higher resolution on page, I don't know, 4, I think, of your handout. So, you know what? Maybe I will not go through it in detail because it's rather messy. But the point is that, well, if you have a node with 6 crossings and 1 rotation number, you end up, so it has sort of 7 features, you end up integrating over r to the 14, and the integrand is the exponential of a Lagrangian, where the Lagrangian comes from local contributions, 1 contribution per crossing, and the contributions are written here. And if you look at these contributions, there is a quadratic part, and then epsilon times a quartic part. So it exactly fits into the picture of perturbed Gaussian integration. And likewise, there is a contribution for the rotation numbers. And in the case of the trefoil, you end up getting this particular integrand. And when you integrate, and Gaussian integrate, perturbed Gaussian integration gives you a specific technique how to integrate. When you integrate, you get, you don't get theta, you get rho 1. To get theta, you do exactly the same, except the Lagrangian is much more complicated. Okay? So again, I'm not going through the details, I'm only telling you the main points. There is a perturbed Gaussian, a finite perturbed Gaussian integral formula for that invariant that I mentioned before.
Sorry, and to get theta, you're cutting off epsilon at a certain power? Or you
So
getting the
theta
whole-
is the epsilon to the 1 coefficient. And in principle, there should be theta 2, which is the contribution of epsilon squared, but we did not compute it yet.
Okay.
Okay? We did compute, however, rho 2. So theta is somehow corresponding to GL3, to SL3, and rho corresponds to SL2. So we did compute rho 2 and rho 3 and maybe even rho 4. So like the technique continues. Okay? Back to the story, back to the diagram. So my hope is to get everything as a co-commutative limit or a solvable approximation, which really means take the story, the old story, and replace G by G sub epsilon, where I've defined G sub epsilon before. So how much of it is done? So basically, like the replacement Chern-Simons to Chern-Simons with G epsilon is straightforward. You just replace G by G epsilon. Okay? G epsilon does not have a representation theory, or does not have an interesting representation theory. So instead of taking the trace in some representation, you simply think of the path-ordered exponential as an element of the universal enveloping algebra, and that totally makes sense. So you don't need a representation. And then, likewise, you can replace the Reshetikhin-Turayev theory with a universal Reshetikhin-Turayev theory with values in the universal enveloping algebra, and then replace the algebra from G to G epsilon, and that totally makes sense. So this is a Talmudic result. This makes sense in the Talmud, not only in the Kabbalah. And likewise, you can take finite type invariants and the Kontsievich integral and configuration space integrals, and if you pick a Lie algebra, that just means that you take these integrals with some specific coefficients that come from that Lie algebra, and it totally makes sense to replace the Lie algebra G by G epsilon. And our hope is to get a triangle like the triangle at the top, but for G epsilon. Now, where are we? So, well, okay. Each of the boxes in its own makes sense. I mean, the top box only in a Kabbalistic sense, the lower boxes in a Talmudic sense. The arrow from this box to this box is more or less understood, and you know, if you want to know more about it, go to a talk I gave in Kyoto or a talk that I gave in Da Nang a few years ago, and read the handout or watch the video. Okay? And we don't really know how to go from here to here, but that's not a big deal because I don't know, I mean, this is not what I care about in a way. I really care about that. Okay? So what I really, really want to know is I want to complete this arrow, going from Chern-Simons theory with G epsilon to the invariants I talked about today. And basically, so this would be perturbation theory applied to Chern-Simons theory, but not where the perturbation parameter is not 1 over k or h bar, but instead epsilon. So k is fixed, or h bar is a constant, and epsilon goes to 0. So at epsilon goes to 0, you should get the Alexander polynomial, but not as a perturbative result, as an exact result. And then beyond that, you should be using perturbation theory in epsilon. And the thing that gets perturbed, again, is not, it's the perturbative term is in the Lie algebra, is in the structure constant. It's not Chern-Simons with a fixed Lie algebra. And yeah, I believe that thing should exist. And I think I'm running out of time, so I will just stop without a more complete justification, and thank the organizers for allowing me to speak.
Maybe one question for George?